begint wil ik even de leden van de jury voorstellen. En dat zijn professor Ramdani van de University of Edinburgh, professor Martens van de KU Leuven. Dan als secretaris hebben we professor Baron. De ondervoorzitter van het comité is professor Pintelon. En dan de promotor is De Naaier en ik zelf ben bij Raillet. Aan u het woord. Hè. Je krijgt dus 45 minuten om het werk dat je gedaan hebt uiteen te zetten. En uiteraard zijn er daarna vragen van de jury. Maar het publiek mag uiteraard ook vragen stellen na de verdediging. Dus als er vragen opkomen tijdens de verdediging, aarzel niet daarna om te stellen. Tom, aan u het woord.
Okay, the talk is in English. So, let's start with a very easy question. You're sitting here, and what are you actually inhaling right now? Air. Air, indeed. It's a thing we love to breathe near the seaside, when we walk in the woods in the Ardennes. It's a thing people love. And when you're healthy, it's very nice to have air around you. But you actually realize what is vital in the air for you. It's also known as the ex-sponsor of Arsenal for the football players. It's what we call oxygen. Because air is a mixture of oxygen and nitrogen. And it's the oxygen that we need. You need it every day. So, if you're healthy, it's nice. Although there's only 20% of the oxygen in the air. So, imagine now the situation like for asthma patients where they really need oxygen often. Even there could be a moment where they are in a lack of oxygen. And then you go to the hospital and then this happens. And at that moment, you have to be really happy that this tube contains the pure oxygen. Because if it would just contain the air, which is here around us, I would say good luck for you. So you need something, you need a technology that we as engineers develop to get pure oxygen into this tube. To make sure that people don't die. And as such, with the pure oxygen, we make people happy again. So the question is now, how do I get the pure oxygen? Well, if you go back to the Middle Ages, what people did was like, we have a mixture, we just boil it, and the components with the lowest boiling point, we get it here. If you make alcohol, what you do is you heat everything up, and the pure alcohol comes into this bottle. Now, why don't we do this for air? Well, the thing is, air is a gas, it's not a liquid. So you would have to go to very low temperatures, meaning like minus 190 degrees. So it would cost a lot of energy to do this, and a lot of money, where there could be actually other options around. And that other option is called adsorption. It means that we will selectively accumulate a certain molecule into the pores of a solid. So in the case of air, what we want is, we will flow air over this solid, which is porous, and the idea is that the nitrogen stays inside the solid, the oxygen goes through the solid, and with that oxygen, I make people happy again, or let them do crazy things like bungee jumping. So what is this solid now? What is this adsorbent? Well, this adsorbent is a porous zeolite. To make it real, it looks like a white powder. It's not cocaine. And then what we do in reality is we press it together to some beads, like kleine knikkertjes. This is when you look at it like this. But on the micro scale, I mean, it looks like this thing. It looks like this on the micro scale. remember the distance from here to here is like about 1 nanometer. It's 10 to the power minus 9 meter. Or idea is, it looks like this. This is another, it's the same structure. But the idea is here, if you look at the gray points, they represent silicium or aluminium. And the middle of the green line is oxygen. So I have like silicium, oxygen, aluminum, oxygen, aluminum, and so on. And the idea is, silicium has the valence 4+, and aluminum the valence 3+. So every time one of the gray dots is an aluminum, there's a negative charge in the framework, and the framework wants to be neutral. So you need counter ions to get a neutral structure. And these are the black or the gray dots in the figure. And these cations, you have to imagine them like marbles, knickers, and they are sitting at fixed positions inside the pores. Okay? So this is the structure of the zeolite when you break it down into the smallest parts. Now, so the idea here is that the nitrogen stays inside these holes and the oxygen goes through the holes. And as such, I get the oxygen. So, adsorption is like a very efficient technique here because it has a lower cost, higher energy efficiency, and it saves lives. So it's worth researching adsorption. Although I didn't explain yet how it works. Why does the nitrogen stay inside the pores and the oxygen goes through? It's rather simple. The idea is that the nitrogen is strongly attracted to the marbles, to the cations. So the nitrogen stays inside and the oxygen goes through. When you make a figure like this on the left, what I do is I make a plot of on the y-axis. It represents the number of molecules inside the pores. And on the x-axis, I plot the pressure of the gas around the solid. So you see clearly that there are more nitrogen molecules than oxygen molecules inside the pores, which means selective adsorption of nitrogen. That mechanism is called the equilibrium separation mechanism. And in industry, there are two other separation mechanisms which are used, called kinetic and steric. For kinetic, it works like this. You take the same pore, and I want to separate molecule A from molecule B. And this A molecule, you see, it fits nicely inside the pores. So it will stay inside. Whereas my molecule B, it has very difficult to get inside. See? It's very hard for it to get in. And as such, I can separate them too. The A molecule goes in, and the B molecule needs a really lot of time to go in, which is shown in the figure there. So A, it's very quick to go in, and B goes only in very, very slowly. And the extreme limit of the kinetic effect is called the steric effect. So when I want to separate the same molecule A, which goes in really nicely, from molecule C, which is this molecule, it never goes in. Never goes in. So A stays in the pores and C goes through. So what we do in reality is we take these beads, we fill like a metal column with those beads, put them inside, then put the mixture, inject it in here, and at the exit I get the pure oxygen. And the nitrogen stays inside the beads which are in the column. Now, this is all really easy and nice and it works, but is there more, is the question. And the answer is yes. There are other separation mechanisms in adsorption which we didn't explore fully yet. And that's the scope of my work. We are going to explore and analyze new or unexplored separation mechanisms. So it means now there will be 3 parts of the talk, that for every part of the talk, we will have an exploration section, like the woman with the binoculars, an analysis section, where you have the woman reading the book, the guy with the machete cracking the case, or you can even look inside the mouth of the crocodile, if you want to go to the end. And for every part, I will add some real-world details, so some context. So these are the 3 parts. In the first part, I will look at what we call chain length dependent adsorption on a zeolitic adsorbent. In the second part, I will look at the mechanisms which are called preferential stacking and breeding. And in the final part, I will investigate the impact of different separation mechanisms, namely equilibrium, kinetic, and what is called the trapdoor effect on one type of zeolites. And the idea is that what we call the leitmotif, which makes the bridges between the different chapters, is the study of the separation mechanism. So we start with part 1, where we are going to look at chain length dependent adsorption. The idea behind this is that we want to more and more make our fuels and our chemicals from renewable sources. And if you do this with fermentation, you end up with a mixture here where the chemicals that you want are inside a big pot with water and other unwanted stuff. So you need to separate the molecules that you want from the mixture. And that's where, in the downstream processing, adsorption comes in. The application I studied here is separation of biobutanol. And biobutanol comes in a water mixture with only 2% of butanol. And that's the chemical I want. So good luck to get it out. Which technique do I need to use then? Well, it has been shown that adsorption, which is in the graph here, AD represents adsorption, it's the most energy and thus cost efficient technique for this recovery. And the process in say, it's like this. So first I need to separate the water with adsorbent 1 and adsorbent 2. And then finally I need to separate the butanol from the other alcohols such as acetone, ethanol, and so on. And that's where my adsorbent SAPO34 comes in. And initially I measure then adsorbed amount as a function of the concentration, which is shown, first exploration. That's me watching sky in northern Australia. This is what I was talking about. These are the isotherms as a function of the liquid concentration. And what you can really see, if you would plot it again, but then because on the left it's in a mass per mass zeolite, and now on the right I plot it as the number of molecules in the pores. You clearly see there are like 2 cutoffs, one between ethanol and propanol, and one between butanol and the higher alcohols. What is the reason for that? For these cutoffs, these changes in capacity? Well, we need to study them. Well, what we do here is to compare the length of the alcohols with the dimensions of the cage. And this is the cage of the adsorbent. So we have a width of 6.7 and a length of 10. And before the first cutoff, I have methanol and ethanol. And they are in my pore along the perpendicular axis, like this. And between the first and the second cutoff, I have propanol and butanol, and they are in the pores not along the perpendicular axis, but along the longitudinal axis. And that causes a cutoff. Like this. They are sitting like this. And finally, for the higher alcohols, the idea is that they are too long to fit along the length. But what they do is they adsorb in a curled, gekromt configuration. And the next step is then, well, if I have this column, if I now continuously inject a mixture of alcohols, do I get pure butanol at the exit or any other alcohol? Can I separate the mixture of alcohols? That's the question. Well, the answer is yes. If you would plot the exit flow rate as a function of the volume that you inject, or it's actually the time, you see that the ethanol always comes out last. It means it stays longer inside the pores. So we have a selective retention of the short chain molecule. And that's the take-home message from part 1. It's with this chain length dependent adsorption, we are able to dynamically separate short chain alcohols from longer chain alcohols with a selective retention of the short chain alcohol. So let's move on to part 2, preferential stacking and reading. Does anybody know this? What are your synthetic clothes made of? I'm not talking about cotton or silk clothes. Huh? If you just grab a shirt, like this shirt, when you look at the label, it will say like 50% cotton and probably 50% something else. What is this? You never look at the label of your clothes? It's polyester, come on. And you have to remember that the basic chemicals to make polyester clothes, it are the same chemicals we need to make the PET bottles or the disposable polystyrene cups. They all come from what we call C8 alkyl aromatic compounds. And these compounds are paraxylane, methaxylane, orthoxylane, and ethylbenzene. All of them are used to make polyesters or the disposable cups you use every day. Now the trick comes. All of them are in the oil that we extract from the earth together. And guess, they all have almost the same boiling point. So good luck with distillation. It's not going to work. So you need adsorption again there to separate them. And what we did in former work in our lab is to measure adsorption isotherms on metal organic frameworks. It's a new type of material, and in say it's just a structure that is built up from metal ion clustered as nodes and organic linkers which link the nodes together. It's shown in that video. One of these MOFs we studied is MIL53, and for MIL53 you see that there are 3 zones. So region 1, the isotherms fall almost together. So I cannot separate the mixture of those 2 components. But you see here, so the 2 components come out at the same time. So this is not a good thing. However, you see for the orthoxylene that suddenly here there's a steep jump and then another plateau region 3. So in my region 3 here, see, clearly the orthoxylene comes out later and I nicely separate the 2 components. And then in region 2, when we see this step, quick step in adsorption amount, which we call reading, then you have something really special in my breakthrough profile. There's an intermediate step. It doesn't happen often. What is the reason for this? Well, let the machete guy crack the case. The idea is that in the first region, you have a so-called closed pore with only one molecule inside the pore. And then in the region 3, the molecule goes open and there are much more, two molecules per channel segment. Or in a picture it goes like this. So at low pressures, so below this pressure, there's no selectivity, so random adsorption. And above that pressure, there's a selective adsorption of the orthoxylene with respect to the ethylbenzene. So the next step is like, okay, this is nice experimental work. Can we actually make a model to describe this? Answer is yes. What we have to do is, for the orthoxylene, which is adsorbed much stronger, I will use a 2-term equation. Namely, the first term is to describe the adsorption in zone 1, and a second term, which I use to describe the adsorption in zone 3 with a step. And for that step, we use what we call a logistic function. So this function will capture the step. And for the ethylbenzene, yeah, it doesn't create a step in the isotherm, so we just use one term. And with this in mind, I now will combine the isotherms with the flow model. Keep in mind that what I actually did here is to make the saturation capacity a function of the pressure or the load. Then I combine it with a mass transfer model and a flow model. And in the end, I will get the different types of profiles. Meaning, at low pressure, there's no selectivity at all. At high pressure, you see the material is selective. And with the model I made, I can capture now the step here in the simulation. It's there. So the main message here is that by combining this loading-dependent saturation capacity with the flow model, I can capture the trends in capacities, selectivities, and breakthrough profiles. I also mentioned the separation mechanism preferential stacking. That means that at low pressure, again, there is non-selective adsorption. But at higher pressure, one of your components will pack in pairs, whereas the other one doesn't. That's what we call preferential stacking. And there is no change in the pore structure. You see here, the diameter of the pore stays the same. But it looks quite similar to breathing, because in breathing, there's like a structural change in my adsorbent. I go from narrow pore to large pore. And here, there's a structural change in my adsorbed phase. So the idea is then, can I do the same? Almost the same. Well, yes. What I do is, I will now implement a loading-dependent adsorption constant. I make this parameter now loading-dependent. Again with the same logistic function. And I only do it for the component that is adsorbed strongest. And it's by a combination of this loading-dependent adsorption constant with my flow model that I will again be able to predict the different trends in capacity, selectivities, and breakthrough profiles. So, in part 3, I have been looking at CO2 methane separation on the zeolite KFI. Maybe first some context, where is this relevant, this CO2 methane separation? Well, methane is a molecule you need every day nowadays. It's the molecule of natural gas. And that's a gas you use in your cooking, your central heating. You can also use it in a bus, for example, that's in Australia, a picture from Australia. All of this is methane, natural gas. It's something, it's probably going to be one of the most important fuels of the future. So you need pure methane in your life. And one of the new ideas is what we call biogas. Biogas is, there are different sources, but you can choose the combination, any combination you want. There are 3 different sources. It can come from animal waste, mist, or organic waste from food factories, or just your homemade organic waste. Then we can just combine it, put it together without oxygen, let the bacteria do their work, and in the end, you will get a gas, which is biogas. And this gas is a mixture of CO2 from methane. And we only need the methane. Yeah, so you need to get the CO2 out of it. And there, we have adsorption coming in again. So if you want to separate CO2 from methane with a zeolite, typically the CO2 is strongly adsorbed. So it means that the CO2 will stay inside the structure and the methane goes through. And you know, so if I inject through the column, in the end, the molecules will, the pores will be filled with CO2. And I need to do something to get the CO2 out again. Otherwise, I can never reuse it. So what I do is, it's called pressure swing adsorption. So initially, I inject the mixture at high pressure. Then the CO2 goes in, and the methane comes out of the column. Then I stop the flow, and then I decrease the pressure, such that the CO2, so I go from here to here, and then the CO2 will come out at the other side of the column. And the difference between the adsorbed amount under desorption and adsorbed amount high pressure is what we call the working capacity of the zeolite. And of course you want this working capacity as high as possible. The zeolite I studied is the KFI zeolite. It looks like this in reality on the microscale. And if you look carefully, there are two types of cages, this one and this one, which if you have too much time, you can make them again. So it looks like this. This is the big cage, which we call alpha cage. And the alpha cage has 8-member twin windows. There are 6 of them. All of them have a diameter of 3.9 angstrom, which you can see there, LTA. This cage. And then you have the bar cage, which is smaller. And you have also 1, 2 flat 8-member twin windows. All of them 3.9 angstrom. And then there are 4, like 1, 2, 3, 4, skewed, gekromd, 8-member twin windows, which is shown here for the gamma cage. And the figure on the right shows the possible location of the cations, the possible location of the marbles in the structure. Now, the goal of the investigation here is to study the CO2 separation potential of the zeolite and the impact of different separation mechanisms. And I don't have enough time now to go through all the work I did on this zeolite, but I will just give some ideas about it. So what I did is I start from the synthesis, then put different cations in the structure, measure low pressure CO2 isotherms, model them, do dynamic experiments, make a performance comparison, and then I do what we call the pressure swing adsorption simulation. So in the end, I actually go from the lowest possible scale, the synthesis, to the highest possible scale, which is the pressure swing adsorption. So it's a lot of information, but to make it easy for you to remember, just remember that you go from the lowest possible scale, from the wallaby to the kangaroo. That's how I remember it. And then, since I was talking about 2 different types of zeolites, I studied one type, which is the low silica form, in which you have a lot of cations, so a lot of marbles in the structure, and one structure with less cations. And then I compare both structures. And the structure with the less cations, which has higher silicium in it, it's called ZK5. So I compare the low silica form with the ZK5 form. And for this ZK5 form, I do the same methodology. So for the ZK5, I follow the same idea from wallaby to kangaroo. So let's look at the most important results. One of the things you should realize is we are looking for the zeolite with the highest working capacity. So if you compare the low silica form and the ZK5 form, you see that low pressure here, the low silica form is high. The white dots are high. Whereas at high pressure, the ZK5 form, the black dots, are higher. So in the end, the ZK5 form has a higher working capacity because the delta N CO2, which refers to the ZK5 form, is bigger than the delta N CO2, which refers to the low silica form. So the ZK5 form is better. That's one thing you have to keep in mind. It has a higher working capacity. And if you go to dynamic experiments, you will see that the ZK5 form, it doesn't only have a higher working capacity, it also has a higher capacity. And that you can just see by looking at the elution time. So if you compare one low silica form with one ZK5 form, you see that the CO2 always comes out later